Welcome to Statistics Tutorial number 3, Statistics for Describing, Exploring, and Comparing Data. This tutorial is designed to reinforce students' abilities to calculate measures of central tendency and variation. Also, we'll be talking about measures of position. If you have a set of data, you're going to want to be able to describe this set of data. One of the things you want to measure is some sort of central tendency. Okay, and then in the next section, we're going to talk about how dispersed the data is, right? Because every single data value is going to be different, so we want to see how spread out it is or how condensed it is, and so forth. So in this case, there are actually many measures of center. Okay, one of them is the mean, and the one that we're going to talk about here is called the arithmetic average. In simple terms, what we're going to do here is just add up all the data values and divide by the number of data values. Now there is a disadvantage to this measure of center, this mean, and that is that it can be easily affected by an outlier. An outlier is a data value that typically is either very large or very small, and it's just not like the others. Okay, it's far away from all the other data values to be kind of singled out. Okay, and what that value does, it'll skew the calculation. Okay, let's talk about some symbols here. This little X with the bar on top of it, that's called the sample mean. Okay, and this is a mean calculated on a sample in particular. Okay, this letter right here, this is actually a Greek letter. It's called mu. And that's the mean, but calculated on a population. So if you have population data, then you just calculate the mean and you give it this symbol. This symbol here is just the summation symbol. That's really more of an operation. Okay, it just tells you that you're going to add a series of numbers. A lowercase n, that is the conventional letter to use for the sample size. Okay, and when you use capital N, that's the convention used for describing the population size. Okay. Again, the context of the problem will tell you whether you're dealing with a sample or a population. And then just X on its own, that's just going to be the variable used to represent the individual data values. Okay. So, like I mentioned before, the arithmetic average, or the mean, as it's also known as, is just simply adding up all your data values and divided by the number of values that you have. Okay. Now, the calculation is done the exact same way whether you're dealing with a sample or a population. And these are the formulas. You're going to add up all the values right here and then divide it by the size, right? And since this is a sample mean, right, that's X bar, you have to divide it by the sample size. Okay. Now the math is exactly the same for population. For the population mean, you're going to add up all the X values and then divided by the population size. Okay, so the method is exactly the same, it's just different symbols here. All right, so for example, if we have this data set, this is our data set. All right, we have 1, 2, 3, 4, 5, 6, 7, 8 values here. In order to calculate, in this case it says to calculate the population mean, we're using mu as a symbol. We're going to sum up all the X values. So we're going to sum up every single value. So this is basically all of this. And our population size, well, that's 8. We counted all those values, right? Add them all up, you get 331 divided by 8, and you get 41.375. So this is supposed to represent the center of this data. Okay, this is one way to represent the center. Again, we're going to talk about other methods of central tendency. Go ahead and pause the video now and try this next example. Okay, so if you were to add up all these values, you get 27 plus 57 plus 39 plus... Okay, if you add up all these values, you get 357 divided by 10 gives you 35.7. Okay, that is the mean. And they did mention it was a sample mean, but again, the calculation is done the same way. All right, the next measure of center that we like to talk about is the median. Okay, what is a median? Well, the median basically represents a value that splits the data set in half. Okay, where this value partitions the data set into half the values are greater than this value and half the values are less than this value. So in order to compute the median of any data set, you have to make sure that you sort the data list from least to greatest. So in this particular case, we have 3, 5, 7, 6, 9. It's not in order, but once you actually sort it, you get 3, 5, 6, 7, 9, right? Now the value that splits the data set in half, well, it's going to be this value 6, right? Because 6, there's 2 values less than that, and there's 2 values greater than that. So 6 is the median. Okay, so there's not much of a calculation to be done there. It's just a matter of sorting your data and identifying the middle value. Okay, well that's if you have an odd number of values. Well, what if you have an even number of values, right? Like in this case. Well, once you sort your data from least to greatest, you have 2, 3, 5, 6, 7, 8. Well, let's see. So for example, well, this middle number, it can either be the 5 or the 6. If it's 5, well, there's 2 values that are less than that and 3 values that are greater than that, so it can't be 5. And if it's 6, again, we have the same issue, 3 values less than that and 2 values greater than that, so it can't be 6 either. Okay, so what it turns out to be is you take those middle 2 values, add them up, and divide by 2. So the median is going to be somewhere in between 5 and 6. Okay. So we're going to add them up, divide by 2, which we get 6 plus 5 is 11, divided by 2 is 5.5, and that's our median. So you notice that 5.5 is not one of the original data values, but it is still considered the median here. It's the value that splits the data set in half. All right, so now go ahead and pause the video and try this next example. Okay. First order of business is to sort the data. And how many values do we have? Well, if I count them, I get 1, 2, 3, 4, 5, 6, 7, 8. All right, so since I know it's 8, half of 8 is 4. So it's not going to be the fourth one, you see? Because if that's the fourth one right there, and that splits it into 3 and 4. So that definitely can't be the median. So it has to be between the fourth and the fifth value. Okay, so it's going to be between these two values. And of course, we have to add these two and divide by 2. We get 128. Divided by 2 is 64. So that's the median. All right. The next measure of center is the mode. Okay, this is just another measure of center. Now this one's a little different because all we're doing here is just figuring out which value occurs the most often. Okay, the one that occurs the most times will be the mode. Okay, now what if there's a tie? Well, then you have essentially 2 modes. If there's a 3-way tie, then you'll have 3 modes, and so on. Okay, so in this particular example, you see how 13 shows up twice, so that is the mode. In this particular example, you have a data set where 4 is repeated 3 times, 7 is repeated 3 times, 9 is also repeated 3 times. 11 is only repeated twice, so that can't be the mode because it's not more than 3. And in this case, well, there's a 3-way tie, so the mode is 4, 7, 9. Okay, go ahead and pause the video and find the mode for this data set here. Okay, so if you go down just one by one, I'll start with 27. Okay, so I see 27 here, 27 there. Okay, so I have a 27 here. That shows up 3 times. We'll see if any other data value shows up 3 or more times. 25 only shows up twice. Okay, so that can't be the mode. 29 shows up only once. 7 shows up 3 times. And then 5 has already been talked about. All right, so in this case, we have, again, a tie between 7 and 27. So we have the mode being 7 and 27. The last measure of center that we're going to talk about is called the mid-range. Okay, now this one's not too hard to do. All you have to do is identify the maximum value and the minimum value, add them up, and divide by 2. Okay. All right, so in this particular example, the minimum value that I see here is 11, even though it shows up twice. Well, it's still the minimum value. The maximum value that I see here is 22. We're going to go ahead and add them up, divide by 2, get 33 divided by 2, and 16.5 is the mid-range. Okay, go ahead and pause the video and find the mid-range for this data set. All right, so the minimum value is 19. That's your minimum. Your largest value, your maximum, is 121. Again, we're going to go ahead and add these values and find the value that's right down the middle. Okay, so add them up. We get 140 divided by 2 is 70. So 70 is the mid-range. Okay, so one last thing on the measures of center. We're going to talk about the shape of a distribution. Okay, so if you recall from chapter 2 tutorial, we dealt with histograms, right? So where values were more frequent, we had taller bars, and where it was less frequent, the bars were shorter. So you can look at these 3 graphs, right? The blue, red, and green. You can think of them as histograms. So it's very similar to histograms here. Okay. But this is dealing with continuous data, not discrete data. Okay. So the one thing I want to know is if you were to create like a histogram and if you have a long right tail, like in the blue one right here, this will be considered skewed to the right. Right skewed. Right. You might think to yourself, well, why, if the peak here is more to the left, then why is it called right skewed? Well, it's because you're really focusing on the tail here. So you see how it has a long right tail as opposed to its short left tail. Okay. Same thing for this green one, it has a long left tail. So this is called left skewed. Okay. And then something that's very symmetrical, where the tails, the left and the right, seem to be going down at the same rate. That's going to be no skewness at all, right? That's going to be a symmetrical distribution. Measures of variation. Okay, so of course, if you have a data set, not every value in your data set is going to be the same, so they will vary from value to value, and this is what's called variation, right? And there needs to be a way to measure this type of variation. Okay, there are a couple ways. One of them is called the range, and this is actually a very quick and easy calculation. And the range is just the difference between your maximum value and your minimum value. So for example, in this data set, we have the largest value that we see here is 57, that's your maximum. And the smallest being 14, that's your minimum. You go ahead and take the difference between those, and 43 will be the range. Okay, so this is a measure of how spread out the data is. Okay, go ahead and pause the video and find the range for the following data set. Okay, so as you can see, the minimum value here would be 21, the maximum being 67. So you would just take 67 minus 21, which is 46, and that is the range. So the reason there's different measures of variation or different measures of center is because that some of these measurements are better than others for certain situations. Okay, so in this particular calculation, you notice that we only took into account 2 values in the entire data set, and all the other values weren't taken into account at all. Okay, so the standard deviation, which is in the next page here, is actually a measure of variation that actually takes every single data value into account. Now, it's kind of a complicated formula, but it's actually not too bad. Okay, there's actually 2 different versions of it. One of them can be done easier than others. I would suggest just going for the first one. It's actually, if you create like a table, you can actually calculate that way. The one thing to note is that if you're dealing with a sample, the calculation for the standard deviation is this thing here. And what you'll notice here is that the denominator is the sample size minus 1. Now, of course, if you're dealing with a population, we use a Greek letter, and that's sigma. That's a lowercase sigma. Okay. And the calculation looks very similar to the one for the sample, right? The population and the sample, they look pretty similar, except for in the denominator, we don't have the sample size, right? It's the population size on its own without the minus 1. Okay, so now the math is pretty much the same other than that denominator. Okay, so that's the one distinction here. Okay, for example, it's asking us to find the standard deviation. Now, it doesn't really specify if this is a sample or a population, but by the way I see the calculation here, we're going to say sample because they are actually calculating the sample standard deviation. So that was just omitted there. Okay, so we have 4 data values. You see that? Okay. Now, what is this formula telling us to do? Well, it's telling us to take each one of these data values, right? These are your x values. This is like your x1, x2, x3, x4. The little numbers there are just subscripts here. We're going to take each one of those data values. Let me go ahead and erase this really quick. Okay, so you're going to take each one of those data values, right, x, and then we're going to subtract off the mean, the sample mean. Okay, so that means we have to calculate the sample mean first. All right, so we take each one of the values, 22, 22, 26, 24, add them up, divided by 4. That's how you would get the sample mean. That's 23.5. Okay. Now we're going to take each one of these values and subtract the mean from it. So these are called deviations here. All these values here. Okay. So you take the 22 minus 23.5 and you get a negative 1.5. You do the same thing with the next 22. Should be the same difference. 26 minus 23.5, you get 2.5, and then 23.5 minus 24, you would get 0.5. Now, the problem here is you might say, oh, okay, now we're going to take these different deviations and then just average them out, right? If you were just to add them all up, divide by 4, you'd be good, right? The problem with that is that some of these are negative and some of these are positive, and when you add up all these deviations, you're always going to get 0. So that's it's useless if all the time that you do this, you're going to get 0. Okay, so what we do instead is we take each one of these deviations and square it. So you'll see that you get that first deviation squared, the second one, the third one, and the fourth one. Okay, so that's why up here you see that we square them. So those are the deviations squared. And then we're going to sum them all up. Okay, we're going to sum them all up. So when we square it, we force it to be a positive number. So summing them all up, that's the summation symbol here. Okay, so we're going to sum them all up. So square them first, sum them all up. And the sum is actually 11. Okay. Now, let me just rewrite this formula and bring this over here. You have S equals square root of the sum of the deviations squared divided by the sample size minus 1. Okay, so far what we have here, this 11 here, this here is the sum of the deviations squared. Okay, now this really shouldn't be an equal sign here, more like an arrow. So now we're going to take, so we have a square root here. We know that this here is this here, so that's the 11 in the numerator. Okay, and your sample size, well, we have 4 values, so it'll be 4 minus 1 gives you 3, and that's how we get essentially this calculation here. That's where that's coming from. And if you run that through your calculator, the standard deviation is 1.915. Okay, so what does this number mean? Well, this 1.915, it's approximately 2. I'm just going to use that for, just to make my point here. It's essentially the average deviation that every single data value has from the mean. Okay, we know that the mean was 23.5. Now each one of these values, on average, is about 2 units away from the 23.5. Okay, so that's kind of the way you want to think of it. It's on average, each value is about 2 units away from the center, from the mean 23.5. Okay, so now you see how this is just kind of all over the place. I would prefer to do it in a more systematic way, and that being using like a table. Okay. All right, so let's actually go ahead and do this next one together. You could do this on your own if you want to pause and do it just the way that we did it up here. But I do want to show you that you can use like a table. Okay, so the first thing to do is to list out all your x values. All right, so we have 5 of them here. Let's make sure that we're accounting for all that here. 25. We have enough room for everything here. 27, 35, and 29. Okay, the next thing is to, well, we first have to calculate the mean here, so the sample mean. If we just do 25 plus 32 plus 27 plus 35 plus 29, all divided by 5. Go ahead and move this out. Well, if you do that calculation, you're going to get 29.6. That's the mean. Okay, that's the sample mean. Okay, so just put that on the side here. All right, so we're going to calculate the deviations next. So you're going to get this x value minus the mean. Okay, so we have 25 minus 29.6, 32 minus 29.6, and so on. And we're going to have the answers here. Okay. And then what we did next was we take each one of these deviations and we square them. So we're going to get that negative 4.6 squared. If you calculate that with the calculator, you get 21.16, and then you just do that for each one of these. Okay, so of course once you square everything, you should always end up getting a positive number. Okay, now finally we have all the square deviations. What we're going to do is we're going to sum all of this. All right, so the sum of the deviations squared, or the squared deviations, is just the sum of these highlighted numbers. If you go ahead and do that, you get 63.2. Okay, so that's what we have so far. And finally, to calculate the standard deviation, it's going to be the square root of the sum of the deviation squared over sample size minus 1. Okay, so in our case, we have the square root. That portion in the numerator is 63.2. Our n, well, our n was 5, right? There's 5 data values. So n minus 1 would be 4. Okay, divide those, you get 15.8. And finally running that through your calculator and rounding to, let me just round to like 3 decimal places. I get something like 3.975 is our sample standard deviation for this data set of 5 values. Now there is a shortcut to get this value, or very close to this value, and that's called the range rule of thumb. Now this doesn't always work precisely. It just kind of gives you an approximation. Okay, that's the range rule of thumb. In order to kind of estimate the standard deviation, for example, if you don't have all access to all the data, what you would do is take the range, which is the largest minus the smallest, so you still would have to have the largest minus the smallest, and just divide that by 4. So it's the range divided by 4. Okay. Now that's, if you have access to all the data, then of course do it the correct way. But if you just have the minimum value and the largest value, you can essentially get to this value pretty close. So in our case, for the previous problem, if you have your range, which would be the maximum minus the minimum, max minus min divided by 4. Well, in our case, maximum was 35, the minimum was 25, so 35 minus 25 over 4, well, that's 10 in the numerator, divided by 4 is 2.5. Now, it's a little subjective to see that these are approximately the same. 2.5 and 3.9, they're fairly close. Okay, it kind of gives you in the ballpark, so it's not perfectly accurate, obviously. Now, if you do have data that is spread out in both directions from the mean, we would call that a symmetrical distribution, which would be bell-shaped, where you have most of the data values are close to the mean. So that means, again, you can think of this as like a histogram. Okay, where the height here of this curve indicates that there's a larger concentration here in this region than there is further away. Like there's less concentration out in the tails here. Okay, with that said, it turns out, now you won't actually be able to find this out until you get to a discussion on normal distributions later on, which is not in this chapter at all. But it turns out that within 1 standard deviation from the mean, so if you get the mean, which is here, and you add on a standard deviation and subtract off a standard deviation, that region will contain 68% of all the observations in your data set. So most of them, about 2/3 of all your data should be in this region here. You see that? About 2/3 should be in there. Okay. And if you increase it to 2 standard deviations here, almost everything, again, 2 standard deviations would be from here to here, and that would encompass 95% of all your observations. And then when you move over to 3 standard deviations away, okay, that gets really close to 100%. You're never going to really get 100%, but you get pretty close to it, and that's at 99.7. So it's most of your data. So there's still a little bit remaining in the tails. Okay. Measures of position. Okay, so we're going to talk about z-scores and what that means. A z-score is essentially the number of standard deviations at any given x value in your data set is either above or below the mean. Okay, depending on what you're dealing with, whether it's a sample or population, the calculation is exactly the same. So here's your data value. We subtract off the mean, and we divide it by the standard deviation, and that gives us the z-score, which again is a measure of how many standard deviations that particular data value is from the mean. Okay, and of course that can be done for the population also, except we have the population mean and the population standard deviation. Okay, so we have an example here. It says, who is relatively taller, a 68-inch man or a 62-inch woman? Okay, so clearly if you just compare the two numbers, the man is taller than the woman, but what we're talking about is relatively taller, meaning to their respective sex, right? So is this 68-inch man taller on the scale compared to all men versus the 62-inch woman taller in comparison to all women? We would have to actually evaluate this using the z-scores. You want to see essentially how far away from the mean each one of these two measurements is, relatively speaking. So the average height for men is 69.9 inches, and the standard deviation being 3.0 inches. And that's for men. Okay, and then for women, the mean height is 64.6 with a standard deviation of 2.8 inches. Okay. All right, so to calculate the z-score for that 68-inch man, well, that's your data value, right? Your x, that's the 68. You subtract off the mean, which is 69.9, and you get a negative 1.9. Okay. Now you divide that by the standard deviation, and that gives you essentially a distance from the mean. Okay. So if we were to have the mean at the center, okay. Now, how far away is the mean from the mean? Well, it's 0 units away, right? And one standard deviation would be 1, 2, 3, right? These are all going to be z-scores. Right? This negative 0.63, that should be somewhere around there. Okay, so it's pretty close to the mean, right? Because the mean is at 0. Now we have to compare this distance, right, for the female, right? So the woman here is 62 inches. Now, if we do the same calculation, but compared to women, right, we have the mean height of a woman is 64.6, and the standard deviation is 2.8. Okay. Now, in this case, we have a z-score of negative 0.93. And again, on the same scale here, if we have 0 here, negative 1 here, negative 2 here, 3 here, 1, 2, 3. This z-score of negative 0.93, that looks to be, it's pretty close to negative 1. I would say it's somewhere around there. Okay. Now this distance is a little bit further from 0 than for the man. Okay. The man is both taller than the woman, but also relatively it is taller than the woman in this particular case. Okay, and the reasoning for that is because it's further to the right on this number line than the woman's z-score, which was right there. All right, so let's do this example here. It says, find the z-score for the following. If the average test score was 75 points with a standard deviation of 11 points, and Karina got 89 points, what is her z-score? Well, again, your z-score is just x minus the mean. Now, it doesn't really matter if this is a population or a sample, because the calculation is done the same way, but I'm guessing since the average test score was 75 points, then we had access to all the data. So I'm going to say that it's a population. It doesn't really matter. Okay, so that test score of 89 is your x, and the mean here was 75, and your standard deviation, as I said, was 11. So if we take the difference here, we get 14 over 11. If you do that calculation, you get approximately 1.27. Okay, now percentiles. What are those? Well, percentiles are essentially measures of location amongst your data set. Okay, and you want to think of percentiles as essentially partitions. Okay, there are actually 99 percentiles. Okay, why 99 and not 100? Well, if you think about it, if you're trying to break something up into 100 pieces, you need to make 99 cuts. For example, let's just think about a very simple example. Let's say we have a Snickers bar that I'm trying to break into 4 equal pieces to share with my friends. Well, how many times do I have to cut it? Well, if I cut it once, I get 2 pieces. If I cut another 2 places, we get 4 pieces in total, right? So there was 1, 2, 3 partitions. So there's always going to be one less partition than the number of pieces. Okay, so that's how you want to think of that. Okay, so how do you find an actual percentile here? In order to find a percentile, the list needs to be ordered, right? It has to be sorted from least to greatest. And the answer is given as a whole percent, like 15 percentile, or it won't be. If you had like a 14.8 that you get, you just round it up, round it to wherever it's at. Okay, so here's the formula. So the percentile of x is we count all the items below x, so strictly below, not including x, divided by the total number of items times 100. Okay. Now, here we have a list, and it's actually sorted from least to greatest. And if you want to find the percentile of this value 9, okay, well, what percentile does that represent? Well, you're going to count all the items below 9, so that is everything below 9 and not including line, so that we have 3, right? And the total number of items here, well, if we count every value here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then you have 10. Okay, 3 divided by 10 is 0.3, and you multiply by 100 in order to get a whole number, or get a number between 0 and 100. Okay, so we say that 9 is the 30th percentile. Okay, what would be the percentile of 18 here? Let me go ahead and erase the highlights. 18, again, this data has to be sorted, so here's 18. That is, there's 10 values, so that's the 9th one. Well, how many values are below that? Well, it's always going to be the number below that. Well, that's 8 of them, right? So you have to do 8 over a total of 10 times 100. Well, 8 divided by 10 is 0.8 times 100 will give you 80. So you say 18 is the 80th percentile. Another way to write this, just like in the previous problem, you can say P with the little subscript 30 is 9. You can say it like that. Same thing for this one. You say P sub 80 is equal to 18. Okay, that's just another notation for that, instead of having to write a whole sentence. Okay, now on the flip side, if you're actually trying to find the position of a certain percentile that you already are interested in, well, how would you be able to locate that? Okay, well, you get that percentile, you essentially divide it by 100. So if it's 80 percentile, you'd say 80 divided by 100. It gives you 0.8. And then multiply by the number of data values. Okay, so again, you want to make sure your data list is in order, right, from least to greatest. And that's what we have here. Okay, if I'm looking for the 40th percentile, right, basically 40% of the way through this data set. Okay, if this is the line, I mean, it seems like 50% would be somewhere around here. Maybe 40% would be somewhere around there. Again, that's not very precise, so we have to do this. All right, so the percentile. So that's 40 percentile. We take that 40, multiply by the count of items here. We have 1, 2, 3, 4, 5, 6, 7. So that's how we get 7. You get 280 divided by 100. You get 2.8. And you're always going to round up, okay? In this particular case, right, to the next whole number. So it'll be 3. Now this is not the value 3, it's the location. So this is essentially the location. So that means we're dealing with 1, 2, 3. 77 is the 40th percentile. So we say P40 is 77. Okay. If we're looking for P63, again, the location here would be percentile is 63 times the count here. Again, we still have 7 values divided by 100. And let's go ahead and do that math. You get 4.41. Again, you're going to go ahead and round up to 5. Okay, so that's the location. So we have to count to 5. So again, we have 1, 2, 3, 4, 5. So it'll be 80. So we say that P63 is 80. So it does appear that like 63% of the way it gets us 80. Okay. Now because of that rounding, you're going to have multiple percentiles that will have the same value here. Okay. The only time you'll have a unique data value for each percentile is when you have more than 100 unique data values. Okay. Now go ahead and pause the video and find the 12th percentile. Again, that's P12. Go ahead and try that out. All right, so again, we're going to find the location of P12. And that's going to be, well, 12 times the number of data values. Again, we still have 7 here. Divided by 100. Well, 12 times 7 gives us 84. Over 100 is 0.84. Again, we're going to have to round up to 1. And 1 is the locator. Okay, so it's just going to be that first one here. So we say the 12th percentile is just the first data value, 57. All right, go ahead and try the next problem here. All right, so again, here, this example, what if we actually, this is an example in which, what if we don't actually get a decimal value? Like in each one of the problems above, we had like 2.8, which really shouldn't be an equal sign. This should be more of an arrow. That rounds up to 3. Same thing here, we have 4.41, which rounded up to 5, 0.84, which rounded up to 1, right? What if we actually get a whole number? How do you deal with that? Well, in this case, if you're looking for the 50th percentile of a list of just 4 values, well, if you do 50 times 4, you get 200. Divided by 100, you get 2. Okay, so how do you deal with that? Well, since the location is a whole number, you must find the average of the second, which that's how we're getting the second, and the next value. So the second and the third entries. So the second one is 7, and the next one is 9. And you just average those two values up, and you get 8. So we say the 50th percentile is 8. Okay, so some value 8 here. Okay, let's try let's try this next one. The 25th percentile. We're trying to look for P25. Let's find the location of that. Well, it's going to be 25 times 4. There's 4 values divided by 100. Well, that's going to be 100 divided by 100, which is just 1. So it's going to be between the first and the next and the second, right? Which is 5 and 7. So you just average those out. 5 plus 7 divided by 2. And we get 6. Okay, so we say that P25 is 6. Okay, so it turns out that there are special percentiles that we call quartiles. And there are 3 quartiles. Again, quark, you can think of that as we're breaking it up into 4 equal pieces. And again, we need to have 3 partitions for those 4 equal pieces. Like if you were breaking up a Snickers bar or candy bar. Okay, Q1, Q2, Q3. Well, the second partition is also known as the median, or the 50th percentile. The first partition, Q1, is this 25th percentile, and the Q3 is the 75th percentile. Okay, so we'll do some problems dealing with that in just a bit. All right, now oftentimes we want to be able to represent an entire data set with some sort of picture. Okay, now if you have a really large data set, you can't really account for all the data values in that picture. So what we do is you come up with something called a 5-number summary that gives you an idea of what your data set looks like. And your 5-number summary is, well, your minimum value and your maximum value, and then your 25th percentile, 50th percentile, and your 75th percentile, which are also known as the first quartile, second quartile, and third quartile. All right, so this is the 25th percentile, the 50th percentile, and the 75th percentile. Okay, so in this example, let's try to figure out what this 5-number summary is. Again, you always want to have this list sorted from least to greatest, so we already have that here. And from this 5-number summary, the easiest ones to identify right away is your minimum and your maximum, right? Especially if it's sorted already. So that's your minimum, nothing too hard there. On the next page, you'll see that we have the maximum already identified. Okay, now for the quartiles, you could do it this way using P25, P50, P75. But I would actually do something different. Okay, now these aren't supposed to be equal signs here. These are just location values. Okay, so these are more like colons. Okay. I would do something different. Okay, so the way you deal with this is, well, to find the median, which I would say Q2 is the easiest one to deal with. That's the median. Let's count the number of data values we have. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 values. Well, 10 divided by 2 is 5. So our median is going to be between the 5th and the 6th value. That's going to be the Q2. Okay. Well, if it's between 25 and 27, you just add those up and divide by 2. Okay, 25, what do we get there? 52 divided by 2, and that's 26. So that's the median. Well, you see how even with the calculation, it can be done that way too. So we get the same answer. The first quartile and the third quartile, a better way of thinking of that is, well, the first quartile can be thought as the median of the first half. Okay, so if you ignore the second half, you're just dealing with these numbers here. You don't include the median. So we have 5 numbers. Well, what would be the median of just these 5 numbers? Well, it should be that middle number there. That's Q1. Okay. So we have an odd number of numbers, so it just turns out to be one of the numbers. Okay. Well, that's 20. Isn't that pretty consistent with the using the location formula? And then same thing here for the third quartile. Well, it's just the median of the second half. Okay. And what would be the median of these 5 numbers? Well, it should be that number right in the middle, 30. Again, it's very consistent with what we have there. Okay. Depending on the situation, one method might be easier than the other. I typically just go with the method I just showed. Okay. And if we come up with a box plot, and what's a box plot? Well, as you see in the beginning, we have that box, and that is your 3 quartiles, and then the minimum and the maximum have these little extensions. We call them whiskers that extend out to those values. Okay. So in this case, if your minimum was 10, your maximum was 33, and then your first, second, and third quartile were here. Okay, and this image here essentially gives you an idea of how your data set, how spread out your data set is. You see how we have a pretty long left tail compared to the right tail. So the data is not perfectly symmetrical. So what we're saying here is that there's the same amount of values here, right? For example, the first quartile, there's essentially like 2 values. There's a 12 somewhere around here. Yeah, we have the same amount of values here, than we have in here, than we have in here, than we have in here. It's just over here. When the spaces are a bit wider, that just means that the data values are just more spread out. And when the spaces are just a little bit closer, that means all the data values are more compact. Okay, now there's a better way to come up with this box plot to make it very, very accurate, which we'll do in the next problem here. All right, so again, your data has to be sorted here from least to greatest. So we have our minimum and our max. Those are the easiest ones to identify. Okay, the next order of business is to do the second quartile, because that's the median. Okay, well, how many values do we have here? So if I count, I'm going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 50% of 12 is 6, right? So the 6th one, 1, 2, 3, 4, 5, 6. So it should be between the 6th and the 7th. You see how we have the same amount of values to the left and to the right of this partition? So Q2 is here, which will be 64 plus 68 divided by 2. And if you do that math, you get 66. So Q2 is 66. Okay. Q1 and Q3 are going to be done similarly. But Q1, again, you think of that as the median of the first half. Okay. There's 6 values there. So unlike the other problem where we actually, one of the values was the first quartile, in this case we have 6 values. So again, 6 divided by 2 is 3. So it's going to be between the 3rd and the 4th, right? That's going to be your Q1. Okay. And then again over here on the right hand side, you have 6 values here, and your third quartile will be halfway through it. So the 6 values there, so you just count to 3, and then it'll be between the 3rd and the 4th. So you can see how these partitions split the data set into 4 equal parts, right? Well, each section has 3 values in each quartile, or in each sector, really. Okay, the quartiles are partitions. Okay, so Q1, we'll have to do the math there. It's going to be 50 plus 58 divided by 2. That's 108 divided by 2, which gives us 54. And then here we have 75 plus 88 divided by 2, which gives us 81.5. So 81.5. All right, how do we come up with the box plot? Well, if you're just kind of winging it and just kind of drawing the box plot without any real effort, it's kind of hard. It'll be hard to get it accurate. Okay, so what you really want to do is come up with a measurement scale. Okay. Now, what I like to do here is I look at the minimum and then I look at the maximum. There's 48 and 95, and I think about a couple numbers that are close to that. So I'll say maybe 50 is close to 48 and 100 is close to 95. So I'm going to draw a number line down here. This will be like my measuring stick. If I say that's 50 and that's 100, I could probably break this up into tens, right? So I can do 60, 70, 80. And of course you can, if you're drawing with a pencil and you don't have this quite right, you can always erase. So like right there, I don't feel like that was really accurate. I want to make sure that this is as equally spaced as possible. Okay, it doesn't have to be perfect, but I'll try my best here. I think that's fine. Okay. All right, so you know what? I can actually break this up into fives too. So if I do like 55, so the more precise this measuring stick we have, the better looking our box plot will be. Okay, of course you can use technology to come up with these box plots too, but we're doing everything by hand right now. Okay. So I want to account for 48. So if I go to the left here, I can get 45. Okay, so that's essentially like our measuring stick. All right. So let's start with 48. Well, 48 it's between 45 and 50, and I'm just gonna kind of eyeball it here. That would be like 48. Seems like that's right. Let's go all the way to the maximum, 95. Well, that's exactly on this hash mark. And then let's go ahead and line up or mark up the quartiles here. So 54, well, that seems to be like right before the 55, right? I like to label it. Second quartile is 66, which should be like right after the 65. And the third quartile is 81.5, or here's 80, 81.5. I'm just gonna eyeball it there. So for the quartiles, you have to draw a box. Right, and we draw whiskers to the maximum and then to the minimum. Okay, so that's my recommendation on trying to get this box plot as accurate as possible. All right, now we're going to talk about outliers. Okay, so how to identify if we have an outlier in our data. So an extreme data value relative to the other data values. So this outlier is not wrong, or it shouldn't be thrown out. But there are specific steps in finding out if any of the data values are outliers. Okay, there could be an explanation for that value being so far away from all the rest of the values, but it's not wrong essentially. Okay, you always have to account for it. In some situations, people do throw them out depending on what they're trying to establish. So it's always on a case-by-case basis. All right. So in order to check for an outlier, you have to follow this procedure here. Come up with the first and third quartile, and we calculate what's called the interquartile range. Okay, and that's just the difference between your third and your second and your first quartile. Okay, that essentially is the range of the middle 50% of the data. Okay, and then we have what we call fences or lower cutoffs and upper cutoffs. So your lower fence and your upper fence, we have this formula for it. Okay, so it's your first quartile minus 1.5 times your interquartile range. And then for the upper cutoff, we have the third quartile plus 1.5 times the interquartile range. And any data value that's not within these lower and upper limits, that's to the left of the lower and to the right of the upper, will be considered outliers. And that's how we determine what an outlier is, at least in this context. Okay, so use the following data set to determine if there are any outliers. Okay, again, you want to have your data sorted, which it is, from least to greatest. And if you calculate the first quartile, well, I mean, the second quartile should be that one, right? And the first quartile should be the median of the first part. It looks like it's just that. And the third quartile is the median of the second half, right? There's only 3 values, so it should be that one, right? I didn't have to do any math to find those values. Interquartile, but you can do the math if you like. Interquartile range, well, you just take the difference there. Well, what's the difference between 12 and 7? That's 5. And the lower cutoff will be Q1 minus 1.5 times 5. So that's 7 minus 1.5 times 5. That's where the 5 comes from. That's the interquartile range. Make sure that you multiply before you subtract. Otherwise, you're not following the order of operations here. And the lower fence would be negative 0.5. And then same thing with the upper cutoff. You get the third quartile. But in this case, we add 1.5 times 5. And we get 19.5. Okay, now do we have any outliers? Well, do we have any values that are less than 0.5? Well, the smallest one that we have is 3. That's not to the left of negative 0.5, right? Let me just kind of draw a number line. Negative 0.5, and your upper is 19.5. You see how every one of our data values is within these 2 limits? So there are no outliers in our data. All right, go ahead and pause the video and try this next one for yourself. All right, so first order of business is to find the quartiles, the first and third. I like to start with the second one, right? So we have 8 values here. If it's an even number, the quartile will be between 2 numbers, right? In this case, 8 divided by 2 is 4, so it'll be between the 4th and the 5th one. That's Q2. Okay, we're not really interested in what that number is for this purposes, but we're going to be able to find the first and the second quartile. So the first quartile will be the median of the first part, so there's only 4 numbers there, so it should be between the second and the third. And that is just going to be 15 plus 16 divided by 2, which is 15.5. And the median of the upper part is the third quartile, and that should be between these 2 values here. And that's going to be 26 plus 30 divided by 2, and that gives us 28. All right, if you take the difference here, 28 minus 20 minus 15.5 is 12.5. And let's go ahead and calculate the lower cutoff, which is the first quartile, which is 15.5 minus 1.5 times 12.5, our interquartile range. And we're going to get a lower cutoff or lower fence of negative 3.25. Okay, it doesn't look like we're going to have any outliers to the left, right? Because our smallest value that we see is 4 and the largest is 45. What about on the upper side? Let's see. Well, our third quartile was that 28. In this case, we're going to add on 1.5 times the interquartile range, which is 12.5. And if you do that math, we get something like 46.75. And yeah, again, our largest value is 45. It's not to the right of 46.75. It was really close. It was really close to being an outlier, but it's not significantly far away from the rest of the pack to be considered an outlier. So no, we have none.